Hello everyone, so my name is Caleb Barba and today I'll be sharing my project titled Light as Guitar Vibrations. So I've always loved playing guitar, and while I was practicing one day I realized something interesting. So when I pluck a string, I'm creating vibrations that move through the air as sound. And in a very real sense, light works very similarly. Both light and sound are forms of waves that carry energy through vibration. And my goal in this project was to be able to explore how the vibration of a guitar string parallels the oscillation of electric charges that generate light. And this shows how art and physics speak the same language, which is the language of waves. So the first thing I want to talk about is the pluck. So when I pluck a string, I'm adding energy to a system, and that energy becomes vibration. And that vibration has a specific frequency. I can play a G chord, and that's a different frequency than a C chord, and that determines what note we hear. So the basic relationship for this is the equation F equals V over 2L, where F is the frequency, V is the wave velocity on the string, and L is the string's length. So the shorter, tighter strings vibrate faster and make higher notes than the lower strings. Now imagine the same thing happening on a much smaller, faster scale with an electron instead of a guitar string. When an electron oscillates back and forth, it shakes a surrounding electric and magnetic field, sending ripples of electromagnetic energy into space, and that's what we see as light. And so here in this visual, we see how plucking a guitar string sends out sound waves, and as an electron, when it moves around, it sends out ripples of electromagnetic energy, and we see electromagnetic waves. So both start with a vibration or disturbance that carries energy outwards, and the sound from my guitar travels as pressure waves, which is just air molecules moving back and forth in the same direction as the wave, and that's called a longitudinal wave. Light, however, is a transverse wave. The electric and magnetic fields vibrate perpendicular to the direction that the wave travels. So the math that describes them looks almost identical. So for the guitar, the wave equation is the second order partial derivative with respect to y is equal to v squared times the second order partial derivative with respect to y. And for light, we use the second order gradient of the electromagnetic field wave is equal to mu naught epsilon naught times the second order derivative of the electric field. And the key difference here is what's vibrating: air molecules for sound and electric and magnetic fields for light. But both are waves, and both carry energy at a speed determined by the properties of their medium. And for light in a vacuum, that speed is c equals 1 over the square root of mu naught epsilon naught, which is the fastest tempo in the universe. And if I tighten a string on my guitar, that's gonna change its length, and it's gonna change its frequency to a pitch that I want to hear, with the low frequency being a deep bass note and a high frequency being a bright treble note. And light behaves almost the exact same way. The frequency of an electromagnetic wave determines its color. And just as a musician plays different notes, nature plays different colors. We see different colors all around us. For example, visible red light is on the lower end of the spectrum, and that has a lower frequency and longer wavelength than blue light, which is on the higher end of the spectrum. And so this relationship, it's pretty simple, with frequency equaling the c over lambda. So color is just like the pitch of light, if you will. Frequency is what gives both sound and light their identity. Now moving on, let's talk about amplitude and volume, which is just energy and motion. When I pluck when I pluck softly, the string only moves a little bit, and that's a small amplitude, and the note sounds quiet. If I pluck harder, I increase the amplitude, and the sound becomes louder. Light intensity works the same way. A stronger oscillation of charges means a larger electric field amplitude, which makes the light appear brighter. In both cases, energy scales with the square of amplitude, and that means doubling the amplitude actually quadruples the energy. In electromagnetics, this energy flow is described by the Poynting vector, and it's a fancy way of saying that light carries energy in the direction it travels, the same way a guitar projects sound forward from its vibrating body. So just as another visual example, when I pluck a string, that sends wave vibrations and waves traveling outward. In the same way electric fields do so as well. So this connection is pretty much everywhere in modern technology. Antennas broadcast by oscillating electric waves. Fiber optic cables send information using pulses of light. And lasers are coherent waves that focus precise energy for communication, measurement, and even surgery. And all of these systems depend on the same principles: vibration, frequency, and energy transfer, just like it is playing a guitar. And whether it's sound, light, or data, waves are how we communicate with the universe. So in conclusion, when I look at my guitar now, I see more than just an instrument, but I see a model of how the universe works. Every note I play echoes the same physics that governs light, radio, and color. When I pluck a string, I make a sound wave, and when you shake an electron, you make light. And as the deeper I've explored this connection, the more I've realized something beautiful. Science and art aren't opposites; they're performing the same exact symphony. They're offering under the same exact physics. And light is music beyond hearing. It's a song written in the language of waves, and the universe itself is the grand instrument playing it.